Hello everyone, welcome to the technical evening on building fluid solvers from scratch. I'm Jeff Late, I'm a senior mathematician at Side Effect Software, where I've been working on fluid solvers for quite a few years. And actually I gave a presentation that was also about building fluid solvers from scratch almost 5 years ago. But we've moved a bit from then, and so hopefully this is more streamlined, and also that presentation is hard to find, so it's good to have a new copy of it. So our agenda today is quickly go over a glossary first, because there's a lot of jargon associated with fluid solvers, and just like with any field. And so just making those points clear from the beginning should make things easier. The second stage will be in Houdini, and I'll go through and just build a volumetric smoke solver. And after that, I'll do what I didn't do 5 years ago, which is build a flip fluid solver, also from scratch. So the glossary terms we have, we'll encounter all these words soon enough. The first 4 or so we'll deal with directly in row, and the rest we'll deal with when we run into them. The most essential part of volume-based fluid solver is, of course, the grids, or voxel arrays, but a lot of people seem to call them grids because that's a lot faster to say. And they look very much like ruled grids. So this is just a raster image moved to the third dimension. So a whole stack of pixels, which you call voxels, and you can store your data in these regularly spaced locations. Now we have 2 special words we tend to use in Houdini for these. Inside the SOPS context we call them volumes, and inside the DOPS context we call them fields. And this is partly to try and keep it clear which one you're working with, because you often jump in between those 2 contexts. So what do you store inside those grids? Well, if I wanted to store something like this mouse, which you can't see if you're looking at this online, but just imagine the mouse on your table, into a grid, one way is to take a series of cross sections, and wherever that mouse is present, you put a white pixel or a 1 value, and wherever it's not present, you put a 0. So you get a whole series of like grayscale sections of a mouse that you can see stacked up to form your actual volume. And so that's a good way of storing data. Except there's a rather interesting better approach, which is to recognize we're missing a lot of data there. Like if it's floating point values we're storing, and we're only using a 1 or 0 value, we could just as well use the sign to determine if we're inside or outside. So negative are on the inside and positive are on the outside, for example. And if we do that, then we can use that floating point value to store additional information. And in signed distance fields, or SDFs, that additional information is the distance to the surface. And so if I'm 8 centimeters away from the mouse, I store an 8 in the voxel. And if I'm 2 centimeters inside the mouse, I store a -2. The big advantage of this over the fog fields is that you can actually store subvoxel crossing points for edges. So that purple line is the edge crossing point of this reconstructed surface. If it's a fog volume storing only 1 or 0, the surface has to move an entire voxel every time you try and evolve or change the surface. But if you store a signed distance field, you can move that surface within a voxel. You can't still have 2 purple lines inside the same voxel, so there still have small features will be erased by this, but you can at least have the solid image move subvoxel smoothly. The other really cool feature about them is that it's really fast to compute your distance to the surface, because after you've built this field, you just look up a value in it and you know how far you are from the surface. And likewise, you can find the direction to the surface very quickly, because that's just the gradient of the field. Of course, the trick, of course, is expensive to build these, and can be tricky to build them with various geometry. But when you do have them, they're very fun to work with. The next distinction I'd like to make is Eulerian versus Lagrangian. And this is often less commonly pointed out than the previous issues, but it's one that I think is important for understanding how the voxel fluid simulation differs considerably from the flip fluid simulation and most particle simulations people are used to. Put it simply, is we have a physical system we evolve, and you have the question, where are you going to store the attributes of that simulation? The Eulerian representation is when we want to store it on fixed grid locations, and the Lagrangian usually means we want to store it on the actual particles themselves, on the material that's actually moving through the simulation. And so in the case of the voxel volume-based solutions, you have a grid that's storing a temperature in each of those voxel locations. But as that smoke plume rises, the where we store the temperature does not change. And so we have to record the new temperature values in each of those grid cells to represent how the fluid moved through that grid cell. Well, as if we had the smoke plume represented with particles, the temperature of those particles will stay the same as they move through the system because they're a property of the actual material, so get advected with it. So most traditional particle systems are on that Lagrangian side of things. The next little bit of jargon is just vector fields versus scalar fields. And vector fields are basically when instead of storing like a grayscale value inside our individual voxel coordinates, we store 3 floats to store a direction and a magnitude, or something like RGB if we're storing color. Or could also be useful for storing, of course, velocity or forces. Scalar fields are the simple case of just a single float per voxel location. So this gives you density, temperature, and it's also very useful for masks when you're trying to say, I want this effect to occur only in a certain region of space. That's where you want to build a scalar field to describe that. So with that jargon out of the way, I can move forward to actually running Houdini and trying to build a smoke solver. And no thank you. So the first thing we have to do to get a smoke solver is, of course, to create some volumes to have some smoke to move around. So I'm going to do this inside Houdini. And I have a nice new Houdini session here. And put down some geometry. And I'm going to put down a volume SOP. The volume SOP is to, as the name implies, creates this nice empty chunk of volume, so one of those grids. And I'm going to increase its sampling up to 75. So there's going to be 75 voxels on each side to make it a nice size. I'm going to give it a name as well, density. Now when I middle click on this volume, we have the pop-up text tells us what named volumes are there and what the resolutions are. Checking the resolutions is always a good idea, because if the resolution gets very big, you run out of memory and things get very slow. So you need to watch your total resolutions. So So now let's put something in this, because an empty blank volume is rather boring. So I'll put a volume VOP down and dive into the volume VOP and do an anti-alias noise. And the anti-alias noise I'm going to hook up to the point position and output the result into the density channel. If I turn on the non-wireframe display, we can see here the resulting bit of smoke. I'm going to promote the frequency parameter from the anti-alias noise, and now I can increase the frequency and see our little bit of galaxy matter. Now in this case, the anti-alias noise is actually turning a number between -1 and 1, and so negative fog values obviously don't show up in the viewport. So I can do a fit operation just to remap this range from say -1 to 1, and now you may not see it, but there is the lower level there. But again, I can increase that cutoff point and find where I might have a nice Swiss cheese block of volume. So having this volume in the viewport displayed as a fog is one option, but you can also extract slices of it using the volume slice. And the volume slice, as the name suggests, will slice out a single plane of the volume, and I can alter where that is and then inspect the actual color values, and of course visualize with different methods. Having constructed a scalar volume, the next question is, what about these vector volumes that I might want, for example, to store a velocity? So I can make another volume called vel, change it to vector, and change its max axis to 75. And again, I have an empty volume. I middle click on this, and we see we actually have 3 volumes inside of it. Inside SOPs, there's all the volumes are actually scalar volumes. So a vector volume is just 3 scalar volumes which are associated together by their name. So vel.x, vel.y, vel.z will refer to the x, y, and z coordinates of a single velocity volume. And again, I want to populate this with something interesting, so volume VOP to the rescue. And I can drop in here, and because we bind, oops, wrong parameter. Because we bind the vex parameters to the named input volumes, I can create a vex parameter called vel, which is of type vector, and this will allow me to write out to the velocity value. And so that's my output velocity. So now I need an actual thing to output, so I'll get a curl noise, which is a nice noise generator for velocities. And if I turn on display, We can see now we have a curl noise. It's hard to tell what that is though, because we're seeing the X, Y, and Z directions all just laid on top of each other. So I can, like before, I can do a volume slice to extract an individual slice, and now we can see it as an RGB value. See, maybe we want a slightly higher frequency here. But it's still kind of hard to tell this sort of abstract art looking device what that means in terms of velocities. So we can also do a volume trail. And the volume trail will take the points of the first input and streak them through the velocity volumes of the second input to generate a set of streamers. And the trail length is a bit long for this one, so I'll shorten that up and change the maximum. And now we have something that's giving us some sense of the swirliness of that actual curl field. Now we have two different ways of visualizing by extracting the actual data. What you can also do is visualize it by merging both the density and the velocity volumes together. And here I'm displaying them as one, so I'm actually seeing 4 volumes all drawn on top of each other. But if I use the volume visualization, I can specify which one of these named volumes is to take each role of the visualization. So for density, I can choose the density field, and for the diffuse, or the color, I can choose the velocity field. And so when I just adjust the density scale a bit to make it, there we go, recook, we get the actual velocity drawn as RGB colors and only drawn where the density field's present. This obviously works better if it's actually a color field I'm working with rather than a velocity field. The next part is to make this move. And to make it move, we want it to change over time. And when we have things we want to have feedback or simulate or change over time, we usually want to move into DOPS land. So let's look at how we go about taking these things and putting them into DOPS. First, I'm going to put down some nulls, and these are just nice convenient placeholders so I can find where I'm referring to these different fields. So one I'll call density, which is the density field, and the other I will call velocity, which, as you can guess, is the velocity field. And now I'll put down a dot net. There's a dot network, and now I'm going to jump into the dot network and build the standard dot network if you're building stuff from scratch. So first I start with an empty object, which is the code hook that I hang everything on. And to show how I'm doing this, I'm going to also switch the desktop over to a technical desktop, which makes it easier for me to bring up a details view to show what's going on. So basically in this expander box just above the text port, you can bring up the details view. And you can see we have a single object here which has no real subdata on it yet. So I'm going to attach some data to it. First thing is a scalar field. And the scalar field's imported from SOP, so I'm going to use the SOP dimensions. And for the actual SOP path, bring in the density. And I want to see what that looks like, so the scalar field visualization lets me show the guide geometry to see what this actually looks like. So there's the fog volume being brought in as a scalar field. Seeing it also show up on the details view as a piece of data called scalar field. I don't want to call it scalar field, I want to call it density, so I'll fix that. Now I do the same procedure but with vector field to bring in our desired vector field. So use SOP dimensions, bring in the velocity volume, and vector field visualization. And again, I can show the guide geometry as streamers based off speed and reduce that viz scale and probably the streamer length. So now if I hit play on this simulation, we're going to see nothing interesting happen because there are no solvers. Solvers are what actually cause things to change from frame to frame. And so I put down a multiple solver, and this forms the backbone for the solver.